We are going.
Okay. Welcome from the IIBA Tampa Bay, Florida Chapter Study Group. This is September 2022. This is our 53rd consecutive class. Welcome. Our mission here is to bridge the gap between industry leaders and business analysts by building partnerships with professionals, educators, and employers so that we may empower, instruct, and engage the BA community. We currently have a worldwide audience, so please understand that we are meeting in Eastern Time. We meet every Tuesday from 7 to 8 p.m. Eastern Time. We also have a meetup address. You can join us on Zoom. Here's our past meeting recordings here in turquoise. We have an IIBA website, our meetup, Facebook, and LinkedIn groups. So we have a variety of ways for you to reach out to us if you have any questions. It is our job to provide you mentorship, answers, direction, networking, resume reviews, whatever we can do to help you in your next step in your career. If you're brand new to being a business analyst, it's our job to help you understand that. If you're an experienced business analyst and you're growing, we want to help you do whatever we can to help you grow. We started out our organization in these meetings, working through the sample test questions from Watermark Learning. We spent about 2 weeks per chapter, maybe 3 weeks depending on the chapter, and we worked our way through those, and then we went into techniques. We now are in our professional series. We've had a variety of professionals come and talk to us about their roles as would be tangent to a business analyst, but as business analysts, it's important for us to understand what their role and responsibilities are, as well as how we can best interact with them, what information we need to provide to them, when we need to pull them into discussions, and what can they offer us in our organization. Once we finish with our professional series, we're going to go back to the Watermark Learning test questions and go through those again. The conversations that we have around the test questions are much more important than just studying the test questions and trying to get the right answer, because that allows each of us that are involved in the conversation to identify why a specific question is written the way it is, or why one of the answers is not exactly what it needs to be the right answer, so that those conversations I really feel are the most valuable part of that. We will continue through the chapters until we get to the end, but I want you to know that Watermark Learning has also given us a discount code. It's Tampa 21. You said it was 20% off whenever you used it?
Yep.
Very good. So if you want to use their sample test questions, if you want to take a class with them, if you want to do their flashcards, whatever you want, you can use this code to get a discount. We are a volunteer-run organization. We have a board that is just volunteers, people that can lean in whenever they have time. And I am also on the board. My name is Thea Raisins. I am the Vice President of Career and Professional Development for the board. This is my LinkedIn ID. If you need to reach me, please reach me through my LinkedIn, because I try to keep all of my professional communications through LinkedIn. We do need more board members. If you have, say, an hour, if you have 5 hours, if you have the ability to take on one of our roles that we currently have on the IIBA Tampa Bay, Florida chapter board, let me know. Not only is it a good experience, it helps our community, and I honestly believe that when you help one person, you help everyone, because they are able to help other people. Bob Churchill is our CBAP in residence, and Yulia is also our new CBAP in residence. Thank you for attending, Yulia. Bob is going to be presenting today, and he's going to be talking about simulations. So Bob, I'm going to turn this over to you and let you present.
All right. Hello, everyone. Can you see that? There we go. All right. So, off like a herd of turtles. So the reason I'm telling you about simulation tonight, not that you're interested in simulation yourselves per se, as business analysts or as people in general, but this is how I learned all this stuff. I did it in a bunch of different industries, and that really taught me how to do everything BAs do and all the other kinds of practitioners. It taught me about discovery, finding out what's going on. It taught me about talking to and communicating with other people, developing software, learning deep knowledge of computer architectures and so on. And it'll illuminate the practice of business analysis quite well. So why do we build and run simulations? Here are the reasons. Either we simulate things because we can do it faster, we can do it where we cannot or should not do it at all. We can try a lot of possibilities in a short time, and we can understand a range of possible outcomes when your processes are stochastic, meaning that they are the result of a lot of events in combination. So there are three major types of simulation. They're analog simulations, and they're basically built with mechanical linkages and things like that, and electrical circuits that stand in for other phenomena. I'll go into that in a second. And there are hybrid simulations, which are combinations. A lot of simulations are based on differential equations. Those are continuous simulations. Computational fluid dynamics, flight of aircraft, flow of heat and fluids, things like that, stress analysis, those are all continuous simulations. Discrete event simulation talk about events, and where continuous simulations tend to run every on consistent time intervals, discrete event simulation processes things at any time when the events happen. And obviously we have combinations of the above. So an early mechanical analog simulator is these Link Pilot training simulators. Singer-Link, which is now S3 Technologies, actually ended up being a competitor to the Westinghouse Nuclear Simulator Division. So, a lot of these companies do a lot of different kinds of simulation. I think when they were doing the bombing raids in Japan, when they were practicing those, they'd fly a camera over 3D mock-ups of the Japanese countryside, and they piped in those images to what the bombardier would see. So they use all kinds of clever and convoluted and complicated mechanical simulations back in the day. this is another fairly famous one. If you go to Sausalito in San Francisco, it's on the far side of the Golden Gate Bridge from the main part of San Francisco. They have this bay model, and they built this to explore a particular thing they wanted to go try out in the San Francisco Bay, and they learned that it was a bad idea. But basically, they were trying to figure out the effects of water evaporating versus flowing in. There's a lot of fascinating stuff that can be discussed about this thing. So that's technically a mechanical type model. So there are, if you do electrical simulations, you can do an analog with, say, fluid in pipes or spring mass and dashpot or shock absorber type mechanical systems, because there are certain phenomena that are analogous in different kinds of systems. You don't need to know the details unless you're a nerd, but those analogs do exist. Mathematicians and engineers have thought about them for a long time, and people did fairly complex stuff just doing analog circuit simulation and monitoring the results with oscilloscopes and voltmeters and whatever. And obviously you can have hybrids again. So applications, sorry, this is covering up part of the display. You can do security and event planning, design and sizing, operations research, real-time control, operator training, and a lot of other things. Economic calculations using simulations. There are limits to these things, but those are all things I did in my career. I did simulation for close to 30 years and kind of wish I was doing it now. So, the main architectural considerations for simulation are continuous versus discrete event. We talked about that. Interactive versus fire and forget. So interactive is like you're playing a video game. You do stuff and it responds and it does stuff, and you can interact with it and change what it does on the fly. Fire and forget means you hit the start button and it does what it does as fast as it can, and then it spits the results out. And they have different uses. Interactive is good for real-time control and operation. A lot of other situations, operator training is the other big use. Everything else you want to just have it run as fast as possible. Real-time versus non-real-time is another one. Single platform versus distributed is another one. So when you do a single platform, it's comparatively simple. If you do it distributed, you have to synchronize all the communication links. And we've talked about that before. All the ways communication comes up between computer systems, between people, between processes, and so on. And if I remember the fifth one, I'll tell you. So this is actually an example, and these are live simulations. Yeah, so that's a continuous simulation of a cross-section of a steel bar heating up as heat is applied to the outside of it, not evenly. It is simulating it lying on kind of on the right side closer to you, and the other one on the right is a discrete event simulation of a throughput system that could be almost anything. All right, I've written a lot about this. If you go to this presentation, you can follow everything I've read about it. You can find it on my website on the portfolio page under presentations, and this is in the BA series number 5. Entitled simulation, and you can click through these slides and follow those links if you want. So a continuous simulation, this is an example of a piping system. There are valves and there are vessels, and the vessels might have different fluids in them. This one has liquid and it's open to the atmosphere or some kind of gas. That's a check valve, only allows fluid to go one way. These are connections to other systems. That's a pump. Those are control elements. That is a pressure sensor. That's an orifice plate which restricts flow. So there are a lot of things. There are equations that govern all this. You can solve them in multiple ways, or like we discussed before, you can build an electrical circuit that is analogous to this and do a pretty good job of analyzing all the same stuff. So as you can see, there's an awful lot you have to know. Imagine doing research to find out about the fluids that flow through these things, the characteristics of all these pieces of equipment, the variables you need to describe them, the calculations you need to perform, the way that is implemented and run and controlled on a computer, and what you want to find out in the real world as a result of simulating all this. So those are absolutely the qualitative and procedural things you do as BAs. And of course you have to talk to people about that. So here is setting up some of the math. You write a series of equations. This, I think, adds flows at the nodes or the intersections between all those connections. And then there's an accepted way to do this, and there's a huge class of engineering problems that fill out these equations in a diagonal that also happen to be symmetric about that diagonal. So a lot of smart mathematicians have figured out ways to let's get rid of half the problem, anything we don't need. There's a faster way to solve it, and you always try to exploit the most efficient mathematical method to do this. Here's another example. This is the equation I used for heating up pieces of steel in a reheat furnace. So you go through the same process. You might have more nodes or different nodes. The biggest one I did was, I think, 21 by 7 in a cross section of fairly large pieces of steel. And when I did an extreme loop unrolling of that, it was something like 10,000 lines of code, which I wrote in about 1 second because it was automatically generated. So that's the way the equations look. The simplified part is on the bottom. There are known ways to solve these, and a lot of ways to do that kind of thing. So here's a very much more complicated system. This was when I was first learning this kind of simulation. This is one of the first models I had to simulate, and it was probably too complex for me, but I got a career's worth of education over 3 years figuring this out. So it was actually a lot of fun. So that was continuous simulation. Discrete event simulation talks about events that happen in any order and at any time interval. So I won't go into it in detail, but you notice these items are happening in time. They're processed in time order. So imagine this piece is processed, and it sets up a future event in the queue. It'll say, all right, some other things have to happen X amount of time in the future, and it'll put it in the right order, and then it'll process whatever is next in time order. So viral simulations and economic simulations tend to run that way. So I ended up implementing a framework for doing discrete event simulation in JavaScript, so it's online. It's a crazy language to do it, but I wanted to teach myself and have something that people could interact with on the website. If you actually, let me just bring the simulation itself up. So that is a real life simulation running. You'll start to see entities coming in. They wait in queues. They get distributed to other queues and processing stations that may be in parallel. And then they exit. So here's the same thing rendered in 3D. And all the parameters of this can be changed. when the thing finishes, which will be in just a few seconds, it'll calculate a lot of end-of-process results that an analyst can look at.
This is very cool, Bob.
All right. So, here's, we're talking about interactive versus fire and forget. So this is a Rapier air defense system I trained on when I was in the Army. I actually wore this helmet and used this device.
It is in service in many forms. Here, tracked Rapier is in action with 8 missiles at instant readiness on an enclosed armored vehicle. Rapier was designed unfailingly to hit the target aircraft so that its warhead would explode internally and not somewhere outside the target. Thus, the missile could be made quite small.
All right, we'll stop that. There are 2 kinds of air defense missiles, for example. An infrared missile will be a fire and forget. Once it locks onto its target, it just flies out and chases the heat signature of that target, and whoever fired it doesn't need to do anything. Interactive means that the ground station actually tracks the target and monitors the missile and sends commands to the missile to make it track down the target. So that's a big difference. Here's another animation. This one is actually a fire and forget animation of a land border crossing. This happened to be an old layout of Ambassador Bridge, which is the busiest commercial land crossing on either U.S. border, and it's between Detroit and Windsor. So another important consideration is real-time versus non-real-time. That is a shot with Wilford Brimley, and I forget his name, very famous actor, in a nuclear power plant simulator in the movie The China Syndrome. And they couldn't film it in a real plant, but it's an interesting movie. These things were built for operator training, and you do things in real time, and you throw one of any of those controls and all the buttons, dials, knobs, alarms, meters, and so on should very close to the way the actual plant would. That's why they built them. Now, if you're simulating the 100 million years of the evolution of a solar system, you want that to be non-real time, right? You don't want to wait around forever while the thing runs. You'll be dead. So that's the difference there. Single platform versus distributed. Think of a game like SimCity that runs on your computer and can do some reasonably complicated things. Whereas if you set up a system that's running on many computers with many processes that all have to talk to each other, it gets a lot more complex. There are different communication protocols that are made to do this. All right, deterministic versus stochastic. That was the fifth architectural consideration. Deterministic means if you started, there was only one output, right? It's just driven by physics. It produces single point results, and now you're done. So stochastic one, or a Monte Carlo simulation, actually assigns different probabilities to every possible event, where something goes, how long it takes, whether this does or does not happen, the type of entity introduced into a system, whether something breaks or not. All those are probabilities instead of, if A, then B. And you have to run these a bunch of times to get a range of results. So if you're doing, for example, a climate model, assuming it's right, or a weather model, you run it and it gives you a result. But if you run a virology model, then it should give you a range of results. And you know that if they don't report them that way, maybe they're lying about something. So I already covered a lot of that. There are a lot of different functions you can create based on observed data. There's a whole science to making up different kinds of curves for different kinds of events, and that's where data collection and talking to subject matter experts and doing discovery come in. You have to make sure you do this accurately in order to have any good understanding of the range of possibilities that can occur. This affects design decisions like what kind of variables you need to describe certain phenomena and so on. And that'll govern the way the implementers will define variables in their code. So model predictive control, here is a simulation I did that actually runs faster than real time and calculates the temperature of slabs of steel as they run through furnaces. You know, these furnaces, these are in Korea, and these sections swivel so you can pump long slabs into these furnaces, which are about 800 feet long each, and they move through, but there's only one rolling mill, so you have these swiveling sections to transfer one from the B caster over to the A furnace and run them all through the rolling mill. So we had to be pretty accurate with that. There was a lot of V&V that had to be done to make sure it controlled properly and represented the situation accurately. So here is an animation of this running. All these parameters are variable. This is showing you the temperature scale used, you can see things heating up as they're moving through the furnace. This is a shuttle-based furnace instead of a swivel furnace. There's a lot of controls here. That was a fun thing to work on. So a typical business can be thought of as a human-in-the-loop simulation, some parts of which may be automated. That's the important thing. So when you describe the current state, that means you discover everything that's going on. You're doing kind of a simulated description of the business. You might not actually implement a simulation, but you'll find out everything that's going on. And you might automate parts of it, but you're figuring out what's going on as humans are interacting with machines and information and customers and so on. Robotic process automation has been around for a long time. It's often used with legacy systems, and that means you have an automated process interact with an existing computer system, and it goes and retrieves the data, kind of acting as a pseudo-human. And like I said, this has been around for almost 30 years and probably longer. So resources required for simulation: you need computing power to do the calculations, memory to store the code and results. Simulations can just pour out tons of data. I know simulations that turn out gigabytes of data that have to be post-processed, and you have to write special code because the files are too big for something like Excel to handle. And you have to be able to get all the input data. You have to have accurate behavioral data. You have to choose the right amount of granularity, and you have to generate outputs in ways that are useful to somebody. What are the limits to simulation? So if we look at some of the things we've talked about before, we can always do things more granularly, and we can do them in smaller time steps. That makes things more accurate, but also it takes longer to run. So if you're thinking about simulating what's going on in a 3D volume, and you start off with 8 nodes and go to, say, a 2 by 2 by 2 grid, and you go to 3 by 3 by 3, it obviously, the calculations in the memory required to do all that get a lot greater very quickly. So you always have to balance it. It's an engineering trade-off between practicality and speed. If we're going to simulate an atom, think about all the characteristics an atom can have, and how you represent the numbers in a computer, and how many atoms it takes to represent those numbers. So obviously it takes a whole bunch of atoms in a computer to do some kind of simulation of an actual atom. So you can't simulate the entire universe in detail. You have to take shortcuts. So you can also think that the simulation of the entire or the universe is an analog simulation of itself. There are a few things, more nerdy things, that go into various stories. So accuracy is based on, can we get data? Are the effects included greater than the margin of error? Sometimes they are, sometimes they aren't. If we leave out an effect or get an effect wrong or find out about a new effect, will it change everything we're doing? If we can match, so one of the things we have to do with the simulation is tune it so it matches reality, right? That's one way to test it. But one thing we have to ask ourselves is, once we're all done, will it really accurately represent some new situation where we don't know the answer? So remember that all simulations are wrong, some are useful. And here I talk about, I won't go into detail, but there are a lot of simulations that are used for public policy, and they all have mistakes in them and really shouldn't be used for the things they're used for. So just because something looks really technical and sciencey doesn't mean it's right, doesn't mean you should trust it, and doesn't mean the people who are using it aren't lying to you. And it's also possible and very often probable that even if you want to do something well, certain techniques just cannot be done well. And that's the end. We made it through. Thank you for listening. Let me know if you have any questions.
I have a question. You mentioned Selenium, and Selenium is a quality assurance tool that allows you to automate website testing and other things. Can you go into that a little bit? Because I think that's the thing that people can relate to. For instance, regression testing. Test it all night long, come into the answers instead of having a whole team of QA people.
Right. Well, I used to, let me see if I can find the right picture. That picture. So I used to program this little blue box in the gray shaded area with the red outline. And when I built those things, I wasn't connected to the other systems, and they may not have even existed yet. So I had to dummy in write programs to talk to my program to provide test data, so I could test the operation of my program. And Selenium does something very similar. Also, if I wanted to run my program and test all the user interface elements, I could write an automated script to go ahead and have and push buttons and see that the right things happen. As it happens, I did it all by hand, but I was so on top of that tool, and it was really tractable at that time, so I can manage it. But automated tools like that really come into their own when you're testing a much higher level of integration. There are a lot more interactions. Systems are much more complex. If you can imagine Amazon.com doing in their CI/CD release train, and if you change one piece of code, then you have to run 5,000 tests on it. You don't want to do that by hand. You want to automate stuff like that. And that's where tools like Selenium, and there are many others, to test every aspect of a running program, that's when they really shine and come into their own. Great question.
You got 3 minutes. Who else has a question?
How do you, hi, can you hear me?
Yes, we can hear you.
Okay, great. So how do you come up with a simulation or draw a simulation exact to a measure? Like, when you're looking at a high level simulation, versus a low level simulation, what is the draw mechanism for simulation?
Well, it depends on the process. So what we wanted to do, for example, when we did cross-border simulations like this, the big thing we really wanted to understand was how long people had to wait. So if we watched what was going on and measured how long it took to do everything and got things physically in the right place and moving at the right speed, we knew that we would generate the right queue length. So there's always some kind of dynamic thing that you can measure. The standard for accuracy in nuclear power plant simulations is 1% at steady state, so everything's running and nothing's changing, and 10% during a transient. So when things change from one state to another, if they're pretty close, not exactly as close, then they figure that's accurate enough for the purpose. So the KPIs and requirements are always different, and you have to understand and negotiate that. That comes from what you need, what's possible, the nature of the simulation technique, and so on. And that all requires industry knowledge and good communication and negotiation.
And so then can we say use Archie? Like, and I really love that. By the way, thank you so much for Archie. That it continues to make the Archie diagram too. I think it's really important, especially for architecture. So I really appreciated that. So do you go with that and continue an animation like Churchill said. So we continue overall architecture, and to innovate from the system. It would have predictive control. Predictive control is a diagram that is, like, I think, essential for business analysts to have. Have you? Is there like a is there like when you when you draw a simulation and to run a simulation exactly, do you document around that also?
Oh yeah, we document every phase of what we do. So this is really, if you're familiar with my 6-phase model, right? So you've talked to the customer, or whether that's internal or external, and you say, what is this thing gonna do? And when you agree on all that, then you go look at the actual system and learn everything about that. And I've done this in zillions of ways. For nuclear power plant simulators, we had a library of 10,000 documents, which are technical drawings, operational manuals, technical specifications, and so on. And we had to model the height and diameter and material of all the pipes. We had to simulate the thermodynamic properties of water, understand the size, volume, and operational characteristics of all the machines. And that's a ton of research. For a simulation like what I'm showing you now, that is talking to people who operate all the booths in there where different processes go, and breaking down hundreds of hours of video of the plant or that facility in operation from like 10 or 12 different cameras that ran over 3 days. So there's a lot of data, as much as you want, and it depends on the nature of the simulation.
Wow, amazing, sir. That was fantastic. 10,000 pages of documentation and...
No, 10,000 documents. Some of those were hundreds of pages long.
Wow, that's fantastic. Thank you, sir. That was really important. That really helped a lot. Thank you, sir. That was amazing. Thank you, ma'am.
We are past time, but I want to just briefly, Bob, talk about why you would do a simulation versus why don't you just do it in real life?
Well, one of the things we needed to do for border crossings is we were always trying to figure out, or the government or the General Services Administration was always trying to handle more traffic and reduce wait times while maintaining safety and security of the country. That's the theory. So we needed to simulate these things to build up a baseline simulation of what's going on at all these border crossings now. We probably modeled almost 100 different border crossings on both sides of both borders, and even one on the southern border of Mexico. And the idea is, if you want to change a design or do a new design, you'll modify this simulation and see how it behaves. So if you see all the green vehicles here in this big parking lot, that used to be all these semi-trucks would have to park here, and the drivers would have to go into a building and wait in line and do customs paperwork. One way they made this port more efficient and reduced the wait times is they automated all that paperwork and fixed it so it could be done off-site before the truck even arrived. So when the truck pulled up to the primary inspection booth, they already had the manifest. They already knew whether they needed to do any further inspections, and they ended up making things a lot faster. So
it saves time and money. You don't have to experiment. You can reach a conclusion a lot faster because you have the simulation.
Yeah, that's the idea. And we could try 50 different things, and you obviously don't want to build that port 50 times and see what works best. If you do it in the computer, you do it that 50 times and and you build it once. There is a border crossing on the border between Canada and the state of Maine. It's the farthest over one interface in New Brunswick. I did the design and sizing verification models for that. And a few years ago, I actually drove across the bridge, and through the inspection facility, I helped do the V&V on. So that was fun.
Well, thank you. Once again, we are past time, but does anybody have any last questions for Bob?
Sorry about the technical difficulties.
It is what it is. We're good. Bob, that was very enlightening.
Yeah, thanks.
Yes, that was.
I always enjoy your talks.
So just know that the upside is there are a lot of landmines you can step on when you're doing your work, and errors can pop up in 1,000 places for 1,000 reasons. And that's why I always emphasize really talking to your people, your implementers, your SMEs, the people actually doing the work, the people doing UI, UX, and get everything right. Because many of these processes are extremely complicated and very sensitive. So the more you know, the more people's knowledge you can make use of, and the more eyeballs you have on things, the more likely you are to build an effective solution.
Right. I do encourage everyone to take a look at Selenium. It's a cool tool. I have a current questionnaire that's got 27 questions. I need to know all of the variations of if they answer this way, what should it look like, and then it would go to testing. Selenium automates a lot of that for you. So it's a cool thing for business analysts to know. Every QA person needs to have it in their tool belt. Okay, guys, we'll see you next week. Next week, we're going to go over the introduction in Chapter 1 of the BABOK using Watermark Learning's test questions. I do request that you read it a couple of times between now and then. The better you know it, the better we're going to do on the test questions, and the more distance we're going to make in getting through to being able to successfully pass the tests. Okay, guys, see y'all next week.
Thank you
so much.
Bye.
You did great, Bob.
Yeah, my voice left it.
Thank you. Good night.